Hello everyone, now it's unmuted. So how are you guys doing? I hope you're all doing amazing. Now we'll be continue working on our Ultralytics 2 ONNX project. So as I discussed in the previous video, if you have watched the live stream, if you have not, go check it out because that will base the foundations for this video. Now we'll be working on our Ultralytics 2 ONNX project. Now if you're aware of it, Ultralytics is not that good for inference because you have to load so many additional things that are only going to be useful for your training but are not at all useful for your inference. Now there comes in ONNX, which has a lower size in terms of the library itself and is really good for your edge computing, as you can be able to create more instances of your image with a lower memory footprint and your inference speed would be amazing. And there is also a lot of language support when it comes to ONNX-Runtime, because I think it is only also supported in C++ and C and stuff like that, but Ultralytics is only available for Python. So we want to create a proper pipeline in MLOps where you want to train on Python so that your training code is super clean. You have some people working on your training that don't have to worry about too much on the coding side, and you have some people who are working on productionization that can work with these amazing tools and get your boost inference speed faster. Now that's what we are doing in this video. We are using Python for both of the cases, but yeah, let's get started with it. Now today we'll continue working on the inference pipeline that we were working on in the previous video. Now previous video ended a bit abruptly because I was going out of time. It was not at all too good planned, still trying to be a bit more professional in it, but yeah, we'll slowly develop that skill. Now today we'll try to explain whatever we left off in the previous video, try to get the preprocessor and postprocessor working, and let's just see. We want the prediction results for the OBB model to be the same for both our uh, original code, which is our Ultralytics, and also for our ONNX inference code that we are writing ourselves. Now there can be some point level differences, which we would accept some point level differences after 3 to 4 decimal digits, because that's just fine. It is only going to be converted into pixel value. That doesn't matter to us. Least count is too low for us. But yeah, at the most of the part we want the results to be same, and this difference can only come because we are using soft NMS instead of standard NMS. Now if you're not aware of these terms, if these all sounds very too much overwhelming for you, too much more information, you have not watched the previous live stream, so go ahead and watch that. Let's get started with it now. So if you remember, this was our YOLO ONNX experiment file where we were working with our ONNX pipeline. Now if you remember a bit, we were using a soft NMS rotate compute, which came from a GitHub repository of an amazing person who wrote this code. By the way, this was the music you were just listening to when the waiting screen was there, and I was just checking out some description from my previous video. You'll love that format. This is basically the timeline that I'm thinking of that we'll be working on in this project. So first of all, we want to get the pre and post processor working for both, for all of our models, which will include our detection model, our bounding box, and our segmentation. Classification is also a task in YOLO. I have not worked with it too much in terms of like YOLO classification, mostly worked with other classification models, but yeah, that's something we'll have to look at. After that, we want to refactor it into a clean API as it is provided by Ultralytics, which you just run. Super simple, super intuitive, small documentation. We want the same thing for our inference API. After that, we want to see if we can improve our speed further by using some techniques in Python, such as using libraries like numpy and stuff. If you're not aware of it, you can start reading about it. I'm also not aware of it, so maybe in the next stream when we sit together, you might be able to tell me more about when I'm getting stuck at it. So this is a cool thing which allows you to improve your Python performance by like JIT, compiling it in JIT, which is just in time compilation, and you can improve your numpy code as such. So we will be using numpy, and I think in soft NMS compute we have used a lot of numpy, just to show you that amazing library that we are using for this. Where is it? Is this the one? Yes, this is it. So yeah, this you can see where there we are using numpy. So we will be experimenting with these kind of things to further boost our performance. And then finally the last task would be, if we can ahead with that, which would be to use Mojo. Now if you're aware of it, it is a bit of a movement that is going on in the AI industry, where Mojo is currently being performing amazingly in terms of, not this Mojo, excuse me, Mojo what, modular, So this company named Modular created a programming language called Mojo, which looks exactly the same like Python. If you use typing hints in Python, then you wouldn't be able to tell the difference between Python and Mojo. Now, we would be wanting to use this Mojo to run our inference, and the amazing part about Mojo is that it can use all of the libraries and frameworks that you currently use in Python, directly importing them. So if I can just show you, if I can see one example here, but okay, we'll be working with it later. You can go through some examples yourself for now. But yeah, point being, it is very similar to Python, and it allows you to use the same libraries that you use in Python, but speeds everything up for you, which is pretty amazing as compared to some other languages that are out there that have a huge steep learning curve just to get some performance boost. But okay, so this was the soft compute we were using by this amazing person, Zhang Gongji. I hope, I'm pretty sure I'm not pronouncing it correctly, but yes, that's me. But okay, without any further distractions, you guys keep joining in. I'll directly start working on it. You can watch it in the video anyway, and we'll be creating a repo for this. So I'll be keeping it open source so that you can add more functionality to it. Maybe we can improve the performance. Maybe we can take the performance even further than Ultralytics YOLO using some post-processing, pre-processing techniques that are available out in the wild. Now, I don't think pre-processing wouldn't work because we would have to change our training pipeline too, and we are only working on inference for now. But yeah, post-processing techniques we can work on. Now, let's get started with the task that we were left on. So previously, we were trying to write this preprocessor, and I just almost skimmed through it because I had worked on this OBB model previously. I did get some decent results, and I was running out of time in the previous video, and because it was not planned, fucking professionalism that we need. But okay, so now we want to do this. So now let's go to the Ultralytics code line by line, try to understand what our preprocessor is, and see if we can improve our performance further. Now, regarding the model training part, it pretty much remains the same. So if I can just show you that part, here you go. So this is our model training. So we have downloaded the dataset. Now we use a sample of it, as I think in our full-fledged dataset we were facing some issues. I did download the zip file to it, which is 1.85 GB. So let me just do one thing first. So what we can do is, first of all, for anyone of you who has not worked with YOLO much and want to also see at the same time that how we actually train a model. So let me just open up this dataset and let's see the formatting that we have here, so that we can train it ourselves. So we will have it training in the parallelly in the background. Till then, we'll start working on our ONNX-Runtime model and see if we can get the same results. So I'll just delete the zip file. I'm just gonna clean it up, and let's see. So you have images, test train val, and you have your labels and train original, val original. What the fuck do you mean by original? I'm not really sure. What? Do we get something? I'm not able to see something. Not me, please. Okay, weird. Can I just see this? Wow, mic is being weird. Okay, we can open it up like this, I guess. The shortcut for this is Control 4 in Mac. For those of you guys who are not aware, it's still loading though. Okay, this looks like it is in standard YOLO format. This looks correct. I'm not sure how train original is different from this. Let's see. So for those of you who are not aware, standard YOLO format is something like you have the class names first, then you have your bounding boxes, and this is the oriented bounding box task. So I think you will have X, Y, W, H, R, which is your X and Y. X and Y represent your like the center of your box. Then your WH is the width and height of the box, and finally you have the R, which is okay. So this is not in YOLO format. So okay, so we'll have to use the train one, which is converted to YOLO format for us. So yeah, as I was telling you, so this is our class name, which is 0. This is our X, Y, W, H, R. Okay, so they have not used XYWHR. They have basically used X1, Y1, X2, Y2, X3, Y3, X4, Y4, which are basically the 4 coordinates for our rectangle. So this is X1, Y1, X2, Y2, X3, Y3, X4, Y4. And both of the models are like both of these formats are fine for our I think Ultralytics YOLO for training does accept this X1, Y1 for bounding boxes, but basically when you get the predictions, you get them in XYWHR, which is your X center, Y center of the box, width and height of the box, and finally you have the rotation for the box. So okay, so we have our data set. We'll quickly get it to training. So I'll just show you how to create the YAML file. Not here. Let's go to VS Code. Here we go. So in training.py itself, we trained a very low key model using only these 4 images, which is not really great for testing because it might be that the model itself is not working really great, and when we see the results we are not sure why this is happening. Is the ONNX the problem, or is the soft NMS fucking it up? Because it can be the case, if the model is too bad, then the confidence scores can be low, and soft NMX might be bringing a large number of changes that we don't expect generally. So okay, so let's go through the first of all, we'll be importing our Ultralytics YOLO, and we'll have to create a okay, so .v1. So we'll create a new file inside of this, which is our data.yaml. Now, to describe a YOLO model to Ultralytics, you need to create a YAML file for it. Now, the standard format is something like this, where you have your paths and your names for your classes. So we'll be having these same names for our classes. I think there are 15 classes in total in .v1 itself. Let me just quickly check that. I hope there's not much difference in terms of classes. Okay, where we are. Can we get that? Dataset. Object category. So yeah, these are the categories you have. Let's just quickly check. So online Python interpreter, comma separated things, print list, where wait, if I can just type. Oh dude, it's like that, is it? Can we just do something? So let's just do it like this. Well, this is how it is, right? So we'll just replace the and with a comma, and we'll just print len vals dot split at comma, and this should give us the length 15. So we have 15 classes. We are correct there. I hope this code made sense to you. This is why you need to use Python to speed up your task. You don't want to count this, come on, coding. But okay, so let's go. So we have the same names of classes. We don't need to download it. We can specify our model, I guess, but we don't necessarily need this. Don't need this kind of documentation. Paths, I'll quickly specify the stand-up path. So let's just copy its path, paste it here. There you go. Inside of this, your images train, correct, that's correct. For validation, you have images val, which is also correct. Let's also have test in here, images test. Without test is optional. I think Ultralytics doesn't run test by itself, but we'll just specify it for now. I'm not sure how many images we have in here. Let's just quickly test the number of training images. Find in folder. No, not like this. Reveal in finder is what I wanted to do. Yeah, we'll just get info. Whoa, 1412 images. This might take a while to train. Okay, let's do one thing. Okay, what I can do is I can upload this to Drive so that we can run the inference on Colab. That way we should be able to use a GPU and shit should be much faster. But I don't want to show you my Google Drive, which makes sense. So let me just not share my screen, and you'll be seeing my face for 2 minutes, but just know I'm just uploading the same folder that we had to my drive. Cool. Let's just quickly get it to uploading. Where is it? Folder upload, documents, Python, YOLO ONNX, Dota v1. Yeah, we just need to upload this. Go back, upload. Yeah, hope you enjoyed watching my face. We have finally uploaded the dataset, and we can watch the face and the screen together now. Now let's go back to see what we want to do here. So yeah, so as I was explaining you earlier, let's just quickly open the Ultralytics code side by side to our ONNX experiment, and let me explain to you what kind of pre-processing they are doing so that we can understand ourselves what is going on inside the hood when you train a Ultralytics model. So here it is getting uploaded. This is the Dota classes. This is the soft NMS compute that we are using, and this is finally the pipeline that we'll be doing for this project. So let's go here. Let's see. So what we wanted to do is, so we load up all of our data, all of our imports basically. Then we open up our random model that we were using for now. So this is the image we are getting. Let's just quickly run inference on this image side by side to see what are the results we are getting originally by the current your Ultralytics model. So let's just have an inference.py here. Yeah, so we just need to copy all of this, and we just need to specify our path, which would be inside runs train 2. I think it's inside train 2, right? Best.onx. Cool. Not even ONNX, we know it to load best.pt. So we loaded our model. Okay, this seems to be a bug. Interesting. Let's see. No such file or directory. Runs OBB, obviously. VS Code sometimes just truncates that and it confuses me. Now what we want to do is model.predict. So our results will be equal to model.predict, and we'll specify our image, which would be inside where would it be? I think datasets, Dota 8, /images, and we paste this finally. Oh shit, and we got it. Oh yeah, it's inside images /val, and finally our data. So this is our, so this, from this we'll get our results. Let me just quickly print them for you guys. You can see, so we have our so inside OBB we'll be having our boxes, and these are all the names of the classes that we have. If I quickly do result.plot, you will be able to see a plot of the results, but it's a bad result. It's a bad plot. They have the font size too large. I don't like this. I think, okay, so we'll have to do result 0 first of all, because we are only passing in a single image, and you're allowed to pass multiple images in batches here, so that's why it gives you a list instead of that. Result.plot. Okay, so we'll do plot.plot result.plot, and this should give us a plot. What happened? I think you'll have to, I'm sure. Correct. So okay, I think this is decent. I think we can work with this. So you're getting these 4 predictions here. So you have the soccer ball field, you have the basketball court, and the confidence seems to be fine enough. So yeah, so this is what your results look like. And if you go inside the results thing, so you'll be able to see, if I print results.obb, you'll be able to see that you have this all of these different formats available. So you have xy, 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 xy. So this n represents basically normalized. So this is x are divided by their width and y are divided by their height. So this is xy, xy, here you just represent the 4 coordinates. So this is more of a bounding box, and xy, whr is your standard output that you get from your final model inference, model prediction, that is. Okay, I hope that made sense. Now let's quickly go and see. So these are the results that we are getting. We get the values for all of these points, which we have. Correct. Now we want to go there, and I think this R is degrees, I guess. Yeah, it doesn't seem to be that much deviated, so I'm pretty sure that it is degrees. Now let's go here in our inference pipeline, open Docker, and see what we can do with this. Oh, just give me a minute. I'm receiving a call. I need to attend this one. Hello. भाई मैं तो YouTube पे हूँ अभी लाइव. हाँ यार, बैड टाइमिंग. ओके बाय. Yeah, sorry for that. Let's get back to it. Now let's see where we are at. So yeah, so we want to go in our models and we want to just check out what our pre-processing looks like in Ultralytics, so we can follow in the same foot. Now you can't get away with pre-processing, you see. You'll have to use their same code, otherwise you will not get the same performance, because the model will be trained on something else and you will be running the inference on something else completely. Now let's see. So in predict, I think we previously managed to find it. So I think it was in some of the base model that they defined, which is good for us. If they had find it in our base predictor, that means that maybe they are not putting much, like they are using the same pre-processing for all of their different models. So we'll have to write preprocessor only once. So let me just show you how the preprocessor works. It's just too lengthy, I guess. But okay, so what they are doing is, let's go through this line by line. So when they call preprocess, so if not tensor, we are not using tensors here, we're not using our torch, we only want to work with numpy, so this doesn't worry us. Now you do some pre-transforms in this. What is pre-transform? Same shapes, letterbox. What does this letterbox do? Yeah, so you get your image shape, you get your scale fill, which I think are all booleans. Scale fill, scale up, center, stride. So scale up is true by default, scale fill is false, and auto is false. Shape by default is 640, 640. Center is true by default, and stride is 32. Okay. Let's see what they do with this. So if labels is none, image labels.get, if image shape, you get the height and width of the image. Now we are doing that. So originally you get your image of 1024, 1024 and 3. You get the height and width. Then we do new shape, which is equal to, okay, if instance new shape. So yeah, this is basically the image size thing that we are doing. So if it is an instant of int, you create it into a tuple. If it is a tuple, you let it be a tuple. Then ratio new to old. So what they are doing here is they are calculating the ratio, like x and y ratios that we want. So yeah, so this is what they have right now. So new shape. So I think this is what we are, okay, so we are doing image size is our new shape and shape is our original image shape. So this is what we are doing here, correct. Now if not scale up, only scale down, do not scale up for better validation. Yeah, so basically when you scale up an image, I think you lose an information because a lot of interpolation happens. The same thing happens in scale down, but it logically makes sense when you're scaling up, you're losing up more information. When you're scaling down, you're just compressing some of the information, so there will be less loss logically. Now let's go to see if scale up, what is it by default. So scale up is true by default, so I think this will not be activated in our case, so we don't need to really worry about this for now. We can have it as a parameter for sure, because we want it to be pretty much the same as they have. Scale up is equal to true, and if not scale up when you want to do this. So then you want to do r is equal to minimum of r comma 1.0. Cool. So now the image will not scale up. New unpad is equal to okay, so you calculated the minimum of these, and then you said your ratio is equal to r comma r for computing your padding. So new padding would be equal to round dot shape into r and int round shape into r. So what you're doing here is that you're calculating your, so you're just trying to calculate how much padding you need to convert your original image into this new image size. So I think what they're doing is, instead of resizing the image directly, they are adding some black pads around your image to get it to the shape that you desire to train the model on, which should not add too much noise in the image in general. So yeah, that makes sense. So that's how you calculate your padding. So after calculating your padding, you calculate the difference in your padding, in the difference in the width and difference on height from your padded image. So what your actual image size should be later on from the original image that you have. Now why are we calculating this between width and height differently? So I think the scenario is that we are storing height comma width here. So this will give us uh, height comma width. That's how they store it in CV2. And once you have this here, new unpad, we are okay. That's kind of weird. Why are we doing this like this? We could have done 0 here and then 1 there to keep it the same, but okay. They have done it like this, so we'll just follow on the same boots, and we can change that if you want to. I mean, it just looks stupid, no? It creates confusion, unnecessary confusion. So you do this. Now your height remains with the height and width remains with the width. So your image size 1 is your width, and you get your height. So that makes more sense to me. Reduces the confusion basically. Now your difference in width and height, you divide it by 2, because I think you want to center the image, so you're dividing it by 2, which makes sense. So here they did that. So but before doing that, where did we lost them? Okay, this we did this, we calculated dwdh, then finally if self dot auto, which is false in our case, so we don't need to worry about it right now. We just take the mode of them with stride. I'm not sure about that. Scale fill, what is scale fill by default? Scale fill is false by default. Again, don't need to worry about that, but I think what they are doing is, to scale the image, they are just filling in the gaps with, or whatever. What is this? Ratio is equal to, I'm not even sure what they are doing there. Weird. So self.center is true. So that's why we have done this division. We can have it here as well if you want to. So self.center. So center is equal to true. So if center, then only we want to do this. Now we finally have it. So what you want to do is, we want to so if your shape -1, so you are basically reversing your shape here. So instead of getting height width, you are getting width height. You don't need to do that now, since we have reversed new unpad itself. Now image would be equal to cv2 dot resize image comma image size interpolation comma is equal to cv2 dot interlinear. Now top comma bottom is equal to int round. Okay, if self dot center else 0. Okay, it makes sense. but you don't want bottom to be 0. It's when it's self.center. Is that the case? You're adding a bit of a margin to the bottom, I think. Okay, bottom and not just bottom and right. Okay, so this is your dw minus 0.1. So basically whatever the difference in height is, so whatever the difference in width or height is, you just want that, and we want to subtract 0.1 from it and round that. Okay, this is kind of weird. I don't understand. Maybe some mathematical formula they figured out that this was somehow improving the performance, because in any way, like, your dh is going to be some pixel values and you're minusing 0.1 from it, so it should round back to the original pixel basically, or original pixel size. I'm not sure how it will change anything, but okay, let's see. So you finally, what you do is you get your image where you, okay, let's see where the image is till now. So this is our image. We have not done much changes to it. We have just resized the image, and once the image is resized, we want to, okay, maybe that's where we were messing up previously. Mistyped the name. Okay, so image comma top comma bottom comma left comma right, cv to the border constant. So okay, so we added a border of on the top bottom left right that we just did. So we some border on the 0.1. It's not even ratio, so I'm not really sure what's happening here. We'll have to, if you know what's happening, please let me know in the comments down below. But it somehow makes sense to them, and we just have to use the same pre-processing as them. We don't really have to worry anything about it, so just let it be. We are just trying to figure out what's going on under the hood here right now. It doesn't really matter. So okay, so now once we have this, we have created our border. If labels will get ratio pad for evaluation. I'm not sure what's happening there, but okay, so you finally, what you do is, so I think this is all that I've done in here. You don't update the image afterwards. This is for your labels, which you don't need to worry about. We don't need to worry about the labels right now. Labels, we are running inference. This is not training. So yeah, evaluation we will not need. Evaluation will run through YOLO itself. So yeah, labels done. So image is done here. So this is the final pre-processing step for image. Now once you have the image, let's go back to the file where we pre-transform basically. So in pre-transform, we just returned letterbox image for x in images. For all the images, we returned our letterbox, and let's just quickly see what our preprocessor looked like. So okay, so you called the image and then you passed it to a stack, np.stack, and then you added a new axis, or made it from RGB to BGR. So CV2 by default reads the images in RGB. So by doing this, we are reversing it back to BGR. At least that's what I think is happening. We might have to print the images in both the cases to be pretty certain, or we can just experiment with the results using both of the conditions. I think they are using to load up the image, they are not using CV2. If they are using pillow, then the case would be different entirely. So that's what I want to be sure about. What are they using? They have CV2 here. I don't think they have pillow. So yeah, then it should be fine. If they are using CV2, then it should be fine for us. So yeah, so where were we? So yeah, they transpose the image. That's what we are doing here. And so this will just bring the channels to the second axis, and this will be our width and height. Then finally we image.to self.device. Now we are not using torch, so we don't need to worry about it. Else image.float. Yeah, do we need this? We are converting it to a contiguous array here, and we are specifying the d type as np.float32. And then they are converting it to torch, sending it to device, then they are converting it as half is necessary, and If not a tensor, they are replacing it. Let's just print our image here, just to once know one of the axes we can print, or maybe some random pix array, because I just want to see what it actually looks like. So, and even the first axis would be our batch. So I think, yeah, let's just print the whole image once and see if it is already, if it needs division by 255 or does it not. So let's just run this. Okay, it did needed a division by 255 to finally get it into float 32. So this is correct. We don't need to print it anymore. And yeah, those are all the pre-processing steps. So I think basically our major mistake in the previous video was of some kind of a naming error we did while copying from the code. So let's see. So we have the weights here, which is our best.onnx. Let's run the inference. So this will give us our inference results. So I insist that you see the first video before watching this video. Otherwise, it will look like that I'm skimming through the code, but actually I've written this code from scratch in the previous video, where I went through all of these things, that how we do when we create our ONNX session, we import this ORT. From ORT we create a inference session where we specify our model path. These quarks are not necessary because these go in the post processing of YOLO, which this will not really work here. And after that you just do session.run and you provide your, so this you have to figure out a little bit, experiment to see how in your ONNX the input is expected. So you need to pass it as a JSON and pass in your input. And yeah, so you could see in the previous video how I went through all of these errors and figure it out. So finally you get your row output, and I transposed it because I think the row output was of the form image comma batches, and I wanted like result comma batches, and I wanted it as batch comma results. I'm pretty sure that's the case. Let me just quickly print row output dot shape just to make sure what's going on. 1 comma 20 comma 8400. So yeah, so this is basically 1 is our batch, 20 is our, so basically when we get our output from the YOLO model, we get the confidence score for all of our classes, and we get our XYWHR for OBB model. Basically for bounding box models you will only get XYWH and your number of classes. So here we have 15 number of classes, hence we get 20 as our output dimension, because 15 is from our classes, 15 confidence scores, and 5 is your XYWHR. Cool. And let's see, so we have our output. So if you see the output shape that we get after doing this, so we are basically removing that batch dimension that we have, which is unnecessary for us as we are only processing a single image for now. We'll do it into batch wise also. We just have to modify our code a little bit, refactor it to allow that, not a big deal. So yeah, so you get your results, you have your 8400 bounding boxes and your 20, which is your dimension of your final output, which I just explained. Now if I run this, you get 16 items to keep, which is not ideal. Now why is that happening? So we are missing on something definitely. We shouldn't have 15 items to keep, because as we saw in our original image, we don't get 15 items, we only get 4 or even 3, I guess. No, 4 over there, right? 1 2 3 4, counting, I know counting. So yeah, so we get 4 items. So we have to see what blunder we are doing here that is causing that issue. So just to explain whatever we have done here, so again we have our 0 1 to 3 as our XYWH, 4 to 18 is our confidence scores, and finally the 19th one is our rotation. So one thing that we might have missed very easily is that we are passing in rotation as directly, but maybe it needs to pass in So yeah, so in soft NMS compute, they say that they require it in degrees. Now, in theta degrees. So, but here we are might be providing in radians. That can be the only issue I can think of right now. I'm not sure if that would be the case. So what we can do is we can quickly print our row output as such, or maybe just the last box. But okay, that will again be very tricky. Um, okay, let's just do one thing. We have these final results, right? Let's print our final result dot shape. Let's see what it looks like. 16 comma 5. So 16. So these are our XYWHR. We want to convert our XYWHR to XYXY for easier printing, for a easier display, because we can directly pass it to Shapely Polygon in as a list of list where we pass in XY, and we should be able to plot it directly. So let's just do that. Let's just write um, WXYWHR2 XY results. So we know the shape is going to be something like n comma 5, and the first row is going to be x and y, wh, and finally we'll have our r. Now how do you convert this to xy? We can take the help of Ultralytics. Basically they should have the rotation thing here, how they basically convert it, or we can just do it ourselves. So for now, just to test the prediction, you can quickly just search for it. I think that should be the easiest way of doing this. Oh, why to write code when you don't really need to? I mean, for practice it is really good to do that. I'll not say it is a bad thing in general, but still. So this is the other way around. So we can just, I think, use the inverse of it. Oh, they're using minimum area triangle, rectangle, is it? I think what we need to do, okay, how are they specifying the angle again? Angle by 180 into pi. So that is radians, isn't it? That is radians, right? So maybe that's what we are missing on. And it needs to be multiplied by np dot pi and divided by 180. No, that will give you radians, which is nothing. So we'll just do this. Yep, that should be good enough. And let's just see if this brings any improvement. Still, we are getting the first 16 as a result. So what are we missing on? We're passing in our confidence score, we're passing in our boxes as we should, we are giving an offset to the images based on their image size. I don't think we changed the image size, so by default it should be 640. We can also check it, so we can just do image dot shape whatever, this should work out. And then let's just print the image shape here as well. One comma 3 comma 640 comma 640. Okay, so you want to do image dot shape 2 basically. Yep, still we are getting the same results. What's happening? What change do we need to do? So you're getting your class course, which is your 4 to 4 plus number of classes, which will be 4 to 19, which should give you 19 not included, 4 included, which is correct. So this should be your classification scores. After this, you calculate your confidence scores. Okay, for each of the ones, you calculate your np.max class code along axis 1. So this should give you like like the number of boxes that you have and another irrelevant dimension. So yeah, number of boxes that you have and your irrelevant dimension. So these ones you get sorted indices for this based on these confidence scores. And yeah, so np.arc sort confidence scores dimension should be 0 by default, and then you get your sorted confidence scores, and you get your classes as well, which you sort again. Boxes you also sort, so that is correct. And then you did you oh you have to pass in the sorted confidence scores, right? And on basis of these sorted classes you need to do this. How do you calculate your offset classes? No. That's I think what's fucking this up. Oh, finally we have 4. Oh my god, did I fix this? Oh yes, so I think those were our issues. We were sorting them, but we were never using the sorted ones. How amazing am I? But okay, so you finally have the final result in the shape that we always wanted it to be. So there are 4 things in there, but we need to still extract what those 4 things are. So how do you convert XYWHR into the ideal format is the question now. There's some maths involved. Let me just open a, what do you want to open for this? JS Paint? Oh, wow, they upgraded it. Oh my god. I want to do that again. I'm sorry. Wow, Christmas everywhere, guys. Winter celebration, winter theme. Nice. Let's see. So what we have is, we have this center, which is our x comma y. And you have your width, and then let me just draw it somewhere else. So you have your width, and you have your height, and it's assume everything is on center, please. I'm drawing with a touchpad here, and so you get this, and finally here I have some rotation. So let's say I'm assuming it's around this, so this is 0 and it is anti-clockwise, so let's say theta is our rotation. We'll also have to check if theta is working correctly or not. I've given it as, oh, I'm assuming it is in radians and I have converted it to, but it should be in radians logically, because I think they are converting it to radians as a pre-processing step. So yeah, it should be in radians. So yeah, so we have this. So we will easily be able to get our x1 y1, x2 y2, x3 y3, x4 y4, and then we'll have to finally convert them, rotate them, assuming this is our origin, by theta. So how would you do that? So you have some vector like this, and you want to rotate it by theta and give me those points. I think there is a simple formula for this. Um, I remember from my JE times. I don't remember the formula though. That sucks. But okay, if we have to even derive the formula ourselves, we can do it, right? So your y is somewhat increased. Assuming this is our example. So you draw this, you draw this. So you have you know this x, right? Assuming this is our origin, right? Yeah. So you know this x, you know it will be rotated by theta. So you want to subtract something from this x. Now that something would be, so if this was, if okay, so we have plus theta here, so we'll need to know this alpha. Oh god. Oh god, do you wanna play around this? Do you wanna do this right now on live stream? Man. Okay, let's see. So what we have is we have this alpha, which would be our this y divided by tan inverse of y by x. T inverse of y by x. Right. And this will be our alpha, and we calculate our alpha. We know this, so we know that this is gonna be our cos alpha. So cos alpha, right? And so yeah, so whatever is this vector's length. So let's say this is, we know this, right? This is gonna be our x square plus y square. And I bet there would be a simpler formula. And so under root of this. So we know this length. Length cos alpha is this thing. Now when we add theta to it, it will become length cos alpha plus theta. So yeah, so this will be our new x, right? So that will be like L cos alpha minus this will be our difference in the length basically. So, or maybe we can just put a ratio to them. So by how much our x will divide, right? Let's just do it in a ratio form. That seems like it will simplify the things further. So what we need is ki when we divide this, so we want our new length. So ratio would be L cos alpha plus theta divided by cos alpha. Now let's remove the L, as it will be L here as well. Cos alpha plus theta is what is this? Cos A plus B. Not sure. I think it's cos A cos B minus sin A sin B. Oh yes. Oh, it's plus. Fuck. Oh yeah. So it's minus. Fuck. J worked. Made me remember something that is so insignificant in life that I can get just by googling, but I still remember it. That's so good. No, it's not as good, but okay. Cos alpha cos theta minus sin alpha. Man, I'm suffering from this. Sin theta. And no, cringe, please. I'm away from you. Don't you divide this. You're left with cos theta minus sin alpha sin theta. And sin alpha by cos alpha will become tan alpha. So this is your final formula. So you need to multiply your x by this to get your new x. And you will have to do same, not same for y, but oh my god, why are you making me do this? Sin alpha plus theta. Fuck you. I mean, you made sense of this, right? We can just derive the formula from here. We know alpha, we know everything. I want to go through this. So let's just say rotate 4 points by alpha in numpy. I bet there will be a rotate function in there. I'll fucking annoyed by looking at this. You can multiply A with a transpose of the rotation matrix. Now where do I get the rotation? Oh, I think I know the rotation matrix. I've just forgotten it.